talk about shapes or conformations of molecules. Why do molecules assume the shapes that they do? Right? We can rotate around most single bonds, and so does it have a preference for one shape over another? A lot of chemical reactivity comes down to the shape of the molecule. Really, I would say the bulk of biochemistry goes back to molecular structure. Structure dictates function. And so this is our first kind of look at thinking about molecules, not just in terms of bond angles and bond strengths like we did previously, but really digging into how these molecules are moving in real life and what they are likely to look like at any point in time. Remember, they're not these little fixed rocks. They're constantly moving and rotating and stretching back and forth. So let's start small. This is ethane. We can think about rotating around this bond, this carbon-carbon bond in ethane. If we rotate around that carbon-carbon bond in ethane, we can really think about it as two extremes. One where these hydrogens are lined up and one where the hydrogens are not lined up. And the easy way to draw that is to use something called Newman projection. In Newman projections, we're kind of using our eyes, creepy eye, to look down the pipe of the molecule. So we look down the pipe of the molecule, what does it look like? And so when I draw a Newman projection, I've got some molecule in front, and then I kind of use broken lines to indicate the molecule behind. So this is a Newman projection. Newman projections make it easy to talk about dihedral angles. So dihedral angles are 4-atom angles. So it would be a hydrogen, carbon, carbon, hydrogen. If I look down that CC bond with my creepy eye, what angle do the hydrogens take? That is a dihedral angle. Again, we can denote it pretty easily in a Newman projection. So here, these are our extremes. We can think about this dihedral angle here as being 0 degrees. And we can think about this dihedral, maybe between these two hydrogens, as being 180. And so this dihedral would end up being 60 degrees. So again, this is how we tend to talk about conformations. We talk about them in terms, we often draw them in Newman projections, and we discuss them in terms of dihedral angle. I've got the free energy for this bond rotation. It's about 3 kilocalories per mole favoring this one, the staggered one. So why is this staggered conformation favored over the eclipsed conformation? Well, I think this is kind of intuitive. Here I've got these hydrogens lining up with each other, and they're bumping into each other, right? These hydrogens have tiny electron clouds that tend to be kind of, there's really no better way to say it rather than bumping into each other. There's electron-electron repulsion between these hydrogens. And so that's destabilizing. Notice that if I line up these two, I'm also lining up these two and these two. So one way to think about this is a little less than 1 kilocalorie per mole per eclipsed hydrogen. Okay? So overall, this is about a 3 kilocalorie per mole favoring this side. So what does that mean? It means that most of the time, if I look at ethane, it's going to look like this and not that. Actually, if I look even closer, what it indicates is that this is a transition state, and that is a potential energy minimum. So here's the potential energy surface for the bond rotation in ethane that we were just looking at. So my x-axis is the dihedral angle. So again, 0, 60, 90, 180, dihedral angle. And my y-axis is potential energy. As we go, you can see there's hills and valleys. The peaks are when the hydrogens are eclipsed. Those are actually transition states between the local minima. The minima are where the hydrogens are staggered, right? And again, the staggered is lower energy because it's got the least repulsion between hydrogens as the molecule can get. So you can imagine that the hotter my temperature is, the more internal energy I have, and the faster this thing can rotate, because the easier it is for it to have the energy to get over that bump. Conversely, the colder it is, the slower the rotation is going to be, because I might not have quite as much energy to get over the hill. And at absolute 0 or thereabouts, we would have so little energy that I would never be able to get over that barrier. And so I would expect to really never have bond rotation in that case. So this is what the potential energy surface looks like. Again, molecules like ethane are sort of always spinning, but most of the time they hang out in these troughs, and they get there via going over those barriers. So now let's level up and talk about butane, C4, a little bit. So I'll show you this diagram. This diagram is also in your textbook or online, anywhere. If you just Google butane conformers, you'll see something like this. And after I go through this, I'll actually show you a little animation where you can help picture what's going on. Okay, so now I've got 4 carbons. And so I'm going to really look down the pipe of carbon 2 and carbon 3. Creepy eye is looking down there. And so I'm really going to be looking at the dihedral angle between those 2 methyl groups, those 2 CH3s. And as you can imagine, CH3 is bigger than hydrogen. And so having 2 big things bump into each other is worse than having 2 little things bump into each other like hydrogens did. More verbiage. Conformer versus conformation. A conformer is a local energy minimum on the surface. So this molecule essentially has 3 conformers. This one, and this one. These 2, 180 and 180, these are the same thing. So 1, 2, and 3, and these 2 are just mirror images of each other. But those are conformers because they're local energy minimum. A conformation is any shape. So any point along this line, infinite number of possible points are conformations. So infinite number of conformations, 3 conformers. The lowest energy conformer is what we call anti. It is staggered, and it has the methyl groups as far away from each other as they can get. The highest energy is probably what you'd expect, is when they're eclipsed and the 2 methyl groups are bumping into each other with sort of maximum bumpage. Sometimes if we want to use a fancy word, we'll call that steric hindrance. Steric hindrance simply means I've got electron-electron repulsion between these 2 things, and it's raising my potential energy. So that's how we spell steric. Notice it's E, it's not EA. And sometimes we'll denote it with these kind of 2 interlocking parentheses here. So this is telling me, okay, these CH3s are kind of close in space to each other, and so they're kind of bumping into each other, and they'd rather not do that. So that is why this eclipsed, what we might call the syn conformation. The syn conformation is very high in energy because of steric hindrance between the methyl groups. Between those 2 extremes, though, we can think a little bit more sophisticatedly. So, for instance, this conformer, like this conformer, is staggered. We call both of these staggered, dihedral angles around 60. But here, I've got those methyls a little bit close in energy, or close in space, rather. So they're close enough where they can have a little bit of electron-electron repulsion. How much? It's about 1 kilocalories worth. And so we call that gauche. White pants after Labor Day. So gauche. So that is a gauche conformer. Again, still staggered, still an energy minimum, but not as low in energy as if those methyl groups are as far away from each other as they can get. And I also have 2 eclipsed conformations that are lower in energy than the syn conformation, simply because here I have a big thing interacting with a small thing. So here, I've got 2 CH3H interactions, there and there, there and there. And those CH3H interactions are just not as bad as when I have the 2 giant things bumping into each other. Okay, so this big on big interaction is worse than 2 sort of big on small interactions. Okay, so again, this is the potential energy surface. There are better pictures in your textbook and other place. Now let's actually look at what this looks like in reality. Here, again, is butane's conformations. This is the potential energy surface I tried to draw earlier. So as you can see, we're going to start at the anti-conformer. It's the lowest energy conformer. And as it goes through this process, it needs to get over this eclipse barrier to get down to this gauche interaction. You can see down the pipe there, the gauche interaction has those methyl groups at a 60-degree angle. Not as bad as eclipsed, but still interacting enough to raise that potential energy. Right? To get to the other side of this plot, we need to fight through this very large methyl-methyl steric interaction. It brings the energy way up there. And then as we continue to rotate, we end up going to the other gauche interaction, right? That's connected by the eclipse. From that gauche interaction, we would need to get through another lower energy eclipsed to get back to the minimum, global minimum, which has the two methyl groups anti to each other.